Good morning. Welcome to our discussion of alkenes. This is the first of two videos in which I'll be talking about the alkene family. Alkenes are otherwise called olefins. And why are they called olefins? They are called olefins, of course, oleum. We know oleum to mean oil. So olefins, that name is given to them on the basis of the fact that when they react with halogens, they form compounds that are oily. They form oily compounds when they react with halogens, and as such, we call them olefins. Alkenes have the general formula CnH2n. The first alkene, the simplest of all of them, is C2H4, and its name is ethene. If you don't call it ethene, you call it ethylene. So ethylene or ethene is the simplest alkene. It has two carbons. Then we have the functional group of alkenes. We actually write that functional group as a carbon to carbon double bond, like that. So the carbon to carbon double bond is the functional group of alkenes, and the two bonds there are different. We say that one of them is a sigma bond, while the other one is a pi bond. Bear in mind that apart from this bond, which is pi, every other bond in an alkene is sigma. So we have pi bonds only at the point of the carbon to carbon double bond. In terms of hybridization, not every carbon in an alkene is sp2. Instead, the carbons that form the double bond are sp2 hybridized, but the other carbons are usually sp3. In terms of shape, alkenes are trigonal. Their bond angle is 120 degrees. And then the type of reaction they undergo is usually electrophilic addition. Are alkenes saturated or unsaturated? Yes, they are unsaturated. Of course, among all the different hydrocarbons, only the alkenes are saturated. On this side, I've tried to remind us that C2 to C4 alkanes are gases, then C5 to C17, just as we saw for alkanes, C5 to C17 alkenes now are liquids, then C18 and above are solids. Then one characteristic that alkenes have, that alkynes also share, is the ability to decolorize bromine water as well as potassium permanganate. At this point, we are going to look at something very important about alkenes, and that is the question of where do we get alkenes from? How are they prepared? We are going to see preparation of alkenes now, and after preparation, we'll look at the reactions that alkenes undergo. Now, two very important reactions that give us alkenes are called dehalogenation and dehydrohalogenation. Dehalogenation and dehydrohalogenation. If we were to explain these terms, D, removal of; dehalogenation, removal of halogens from a compound. Then dehydrohalogenation means the removal of both hydrogen and halogens from a compound. Now, if we were to carry out dehalogenation or dehydrohalogenation, what reagents would we use? You see, typically, if an organic compound were to undergo a reaction, the reaction would typically involve the organic compound interacting with a certain reagent. So for dehalogenation and dehydrohalogenation, we will have our starting materials, which are organic compounds, and then they will interact with certain reagents that we'll see shortly to give us our desired products. In this case, the desired product is, yes, an alkane. So coming back here, dehalogenation can be achieved using zinc dust in methanol. So zinc dust in methanol is the reagent we commonly employ when we want to carry out dehalogenation. But for dehydrohalogenation, we use potassium hydroxide and ethanol. As a matter of fact, in the absence of potassium hydroxide, sodium hydroxide may also be used. So we just need a caustic alkali and ethanol to carry out dehydrohalogenation. Now, what is our starting material for these two reactions? What kind of compound will I dehalogenate to get an alkene? And what kind of compound will I dehydrohalogenate to get an alkene? Well, in the first case for dehalogenation, I'll need to use a compound that looks somewhat like this. This compound has two halogen atoms on two consecutive carbons. It doesn't just have two halogens, but the two halogens are on consecutive carbons. Now, because it has two halogens at all, it is referred to as a dihalide. So any compound like this with two halogens attached, we call it a dihalide. But that the two halogens are on successive carbons or consecutive carbons means that we are going to add the word vicinal. So what's a vicinal dihalide? A dihalide that has its two halogens on consecutive carbons. But what if the halogens are not on consecutive carbons? In other words, any other arrangement apart from what you are seeing now, consecutive carbons, you refer to the dihalide as being germinal. So a germinal dihalide is simply any dihalide that is not vicinal. So it's like having two extremes. You're either here or there. So we have a clear definition for this on consecutive carbons. Now, if this substance is treated with zinc in methanol, then we expect to get C and C with double bonds, CH3. So if you look at that product now, what appears to have happened? What change do you see? The two halogens up here have been removed. Of course, that's why we call the reaction dehalogenation. And how were they removed? Without going into too much details, we could just say that the zinc here was able to collect the two halogens, was able to cut them off, so that in the end we have a double bond here now, and that product will be called but2-ene. But2-ene may also be called 2-butene. Both names stand for the same substance. So, dehalogenation of vicinal dihalides gives alkenes. What about dehydrohalogenation? In this case, what we require is just an alkyl halide. Alkyl halides are compounds of formula Rx. So once I have an alkyl halide, I am able to dehalogenate it, and that would give me an alkene. Now look at this alkyl halide. You need to listen to this reaction because it has some peculiarities. This is an alkyl halide, so I have Cl there, I have H here, let's say H here. Of course, the other hydrogens have not been indicated, I've not shown them, but we know that there are hydrogens on all of these points. Now, for this compound, if it is subjected to treatment with a caustic alkali and ethanol, so I've written ethanol in shorthand. This is ethyl alcohol. Ethyl alcohol is the trivial name for ethanol. So we can write it like this actually. Now when this reagent is used to treat this compound, what takes place is dehydrohalogenation. So as a matter of fact, whether the compound will undergo dehalogenation or dehydrohalogenation depends on the reagent used to treat it. So with this reagent, we said there will be dehydrohalogenation, which means our KOH is going to cut off this time hydrogen and halogen, and the two of them must come from consecutive carbons. Removing hydrogen and halogen, of course, halogen must come from this carbon. That's the only halogen we have. But can we take hydrogen from here? No. We said the two of them must come from consecutive carbons. It means therefore that when halogen leaves here, the hydrogen has to leave from there, so that our double bond will be at this point. That's easy to determine. Of course, with chlorine off from there, the only next carbon where hydrogen could come from is here. But what if our compound were this way? Imagine having this now. What would happen? Of course, we know where to take the chlorine from, dehalogenation. But for the hydrogen, there are two options now. We could take from carbon 1, but then we could also take from carbon 3. If we were to take from carbon 1, it means our double bond will be here. And if we were to take from carbon 3, it means our double bond will be in the middle there. Which is the better position to take hydrogen from? That will be determined by a certain rule that we refer to as the rule of Zaitsev. So we'll call it Zaitsev's rule. In some other context, this Zaitsev is written as Zaitsev. So you may hear of Zaitsev's rule or Zaitsev's rule. Both spellings are allowed for the name Zaitsev. So Zaitsev's rule, what does it say? Zaitsev's rule guides us when we carry out elimination reactions like this one. It tells us where to, make our elimination occur from. Like in this case, I'm going to remove chlorine from here. That's not negotiable. But where will hydrogen come from? Carbon 1 or carbon 3? Well, Zaitsev's rule says that I should pick hydrogen from the carbon atom that has fewer hydrogens. So looking at carbons 1 and 3, carbon 1 has 3 hydrogens, 1, 2, and 3. But carbon 3 has only 2 hydrogens, 1 and 2. So by Zaitsev's rule, it is better for me to pick my hydrogen from carbon 3. And when I do so, I'll get this as product. The same but2in that we got up there, but2in, that's the product I obtained. But what if I had done the opposite of what Zaitsev suggested? That is taking from carbon 1. It means that my product would have been this, but1in. Well, in real life, if this reaction were to take place, both products will be formed. We'll have both of them as products in real life now. And this upper one would predominate. We'll call it the major product, while we'll call that the minor product. What do we mean? It means that if we have 100% product, this will make up more than 50%. It will predominate, it will be more abundant, whereas this will make up less than 50%. So we'll call it the minor product, whereas that is the major product. So each time we apply Zaitsev's rule, the product predicted by Zaitsev's rule is referred to as the major product. We looked at dehalogenation and dehydrohalogenation. The two of them belong to a class of reactions that we may refer to as elimination reactions. Now here's another elimination reaction we're about to discuss. It's called dehydration of alcohols. Dehydration, what does it mean? It means the removal of water from a substance. Now when an alcohol is dehydrated, think about it. The general formula of alcohols is written as CnH2n plus 1OH. This may be rewritten as CnH2nHOH. So that if we remove water from here, H2O, we are left with CnH2n. So that shows us that when an alcohol is dehydrated, we get an alkene. Now, if you are given a question like this, of course, on the arrow now, we see H2SO4, which is a dehydrating agent. So this alcohol is being treated with a dehydrating agent in the presence of heat. So this signifies heat. What will happen during this reaction? Here we already said water will be driven off, but the water will be driven off as H and OH. Where OH will be eliminated from is not a problem. We already see the OH waiting to be eliminated. But what we have as challenge now is where the hydrogen will come from. Would the hydrogen come from carbon 1 or would it come from carbon 3? In real life, once again, both events will take place, but one of the products will predominate. Which one? As predicted by Sedzev's rule, once again, it is that product where hydrogen is removed from carbon 3 that will predominate. That means our predominant or major product will be this one. This will be our predominant or major product. It is called but2-in. So but2-in is our predominant or major product, whereas but1-in will also be formed, but it will be the minor product. So leaving elimination as a way of making alkenes, the next method of making alkenes that I'm going to talk about is hydrogenation. Hydrogenation of what? Hydrogenation of alkynes. Alkynes can be hydrogenated. That is, when you have CnH2n minus 2, that's an alkyne. By the time you add hydrogens to it, just 2 hydrogens, you are going to get CnH2n. But the truth is, if you were to hydrogenate an alkyne, what would normally happen is the alkyne becomes an alkene first, but ultimately becomes an alkane. So if we must go from alkyne to alkene to alkane, it will be a very simple process, just hydrogenate. However, we are looking at alkenes now, so we are looking at the possibility of this reaction stopping at this level. How do we achieve that? Now, there are 2 easy ways of converting an alkyne into an alkene without getting alkane. One of them involves the use of a modified catalyst called a Lindlar catalyst. And then the second method involves using sodium metal and liquid ammonia. So sodium in liquid ammonia can be used for the hydrogenation of alkynes in order to get alkenes. We can write equations to represent these 2 reactions. This is halogenation. I have written 4 equations, but I'd like to explain them in 2s. So we look at the first 2. Those first 2 are different from the other 2 in that if you look at the first 2, you see how the alkene functional group, that's the carbon-to-carbon triple bond, is placed compared to the lower 2. Now here's the difference. For the lower 2, the carbon-to-carbon triple bond sits on the first carbon. And when you have an alkyne like that, you describe the alkyne as being terminal. So a terminal alkyne is one that has the carbon-to-carbon triple bond on the extreme. Whereas, if the carbon-to-carbon double bond is not on the extreme, I didn't say in the middle now, not on the extreme carbon, we describe the alkyne as being median. So alkynes could be median or terminal, depending on whether or not the carbon-to-carbon double bond is at the extreme carbon. If it's at the extreme, it's terminal, otherwise it's median. So up here, we're looking at median alkynes undergoing these 2 reactions, and then terminal alkynes undergoing the same reactions. In the upper case, what do we see? This is a median alkyne reacting with palladium, with hydrogen basically, but that hydrogen is reacting with it in the presence of a modified catalyst of palladium. That catalyst is seated on barium sulfate and poisoned with powdered sulfur. By the time this reaction is performed, we get an alkene. This alkene is called but2-in. And if you check what's changed, what has really happened here, hydrogen has been added. So as a matter of fact, the reaction we are looking at is called hydrogenation. Like we said, this is hydrogenation. We are adding hydrogen to an alkyne. So two hydrogens have been added here, and there they are, the two hydrogens. In this lower case as well, you see that these two middle carbons have acquired hydrogens. So it means that for these two reactions, where we use palladium with barium sulfate and sulfur, and the reaction where we use sodium in liquid ammonia, the same change took place. And what's that change? The introduction of two hydrogens to the carbons of the double bond. But is there a difference between those two products? Yes, their configuration. Stereoscopically, those two compounds are different. If you look at the upper one, we say it's in the cis configuration, whereas the lower one is in the trans configuration. So when we use sodium in liquid ammonia to treat a median alkyne, then we get a trans alkene. But when we use Lindlar's catalyst to treat a median alkyne, then we get a cis alkene. On the other hand, if our alkyne is terminal, when we treat it with the Lindlar's catalyst, we get an alkene that we cannot classify as cis or trans. If you look at this alkene as it is, you can't call it cis or trans. It's both one in. But in this second case, when we use our terminal alkyne, like we did in the other case, and this time around we treat it with sodium in liquid ammonia. Terminal sodium in liquid ammonia, you don't get alkyne at all. What you get is a compound that we can refer to as an acetylide. We get an acetylide. That acetylide is a substitution product, which means while the other three reactions are addition reactions in that hydrogen is introduced, this one is a substitution reaction. The triple bond doesn't change. See, the other cases, triple has become double. That's addition. But here, the triple bond remains. The only change that takes place is one hydrogen leaves to be replaced by sodium, and that is what substitution means. So this last one is a substitution reaction. When terminal alkynes meet sodium in liquid ammonia, what occurs is a substitution. This product can be named in any of the following two ways. I can call it sodium butylide. Sodium butylide. Remember, it has 4 carbons, both. But in the alternative, I could call it sodium for this, ethyl, then for that, acetylide. So sodium ethyl acetylide or sodium butylide. Any of those two names will apply to this compound. These are some ways of making alkenes. They are very important methods. So I'll leave preparation of alkenes now, so that in our second video, alkenes 2, we'll be looking at the reactions that alkenes undergo.